Okay, thanks. Yeah, so yes, I can share my screen so that I can just show us also how we started that. So the goal of yesterday's class was to, decode from scratch, right? And the idea was to, implement a simple linear regression model, right? For, to solve this, to kind of predict, the maximum temperature from the minimum temperature. So yesterday was just, very simple illustration of, how these algorithms can work and the whole idea. So we have your data set first. You prepare the data set already. You know what you want. We want, in this case, we want just these two, these two variables for the problem statement yesterday, right? And we just want to use this minimum temperature to predict maximum temperature. That's it. And, already you know what. So we just did some peer plots and, we did some data splitting. So here, someone asked this question in the group: why do I use this capital X, as X? And I answered that usually it's a notation. It's a kind of, standard notation in math that X stands for, capital letters. Apart from, in statistics also, it could mean random variable or something. But usually we want to denote X as, as a matrix. And why it is a matrix? Because, we could have more than one feature, right? And I think I can just quickly show us then, because today we would be doing something more, we'll be using more than one feature for our problem today. And so that we can have an idea of, of what I'm talking about. So here, I just selected, I just created a new data frame because the original data frame, like this weather CSV, is a lot, right? And I don't want to work with all of these data frames, all of these features. So I just, created a new data frame and I just selected the two, right? And, it's, I just printed it and this is what we have. Now, this is our X, this is our predictor, and this is what we want to predict, right? So that is, we are using this information to predict the maximum temperature. And, here we check the data type and we just did a pair plot. I don't have to do that. But now my main focus is this place. So here, when we select, minimum temperature for X, which is the predictor, and we select the maximum temperature, Y, which is what we want to predict, then, you can just easily add this. But there is something you have to note, there is something you have to understand that usually, in particular, for, a mutually exclusive, scenarios where, okay, so this is, so this is not the logistic classification problem. But of course, we just expect one output. And usually what you always see is that, you have some function F, takes on some, some kind of matrix value, let's say, kind of D by D, whatever. And, it maps it to just, a real number, something like that, right? And, usually this is what you always want, right? Because the, we just want to output one number, that is the prediction, the prediction. And this somehow can just be a matrix of, kind of metrics of more than for D number of columns, or I can just use N by an M, number of features. But in this case, we just have one feature, right? And if we check the shape of this, of the X, you find out that our X is just 119,040 by 1. And this one is just because it's one feature, which is minimum temperature. And so let us check the shape of Y. So you always find Y also in this form, but usually, because like I said, we can only have one output. So we can just say, okay, we can just call this a vector because we cannot have more than one output, right? And also, it doesn't matter if there is an extra dimension, one or not, it's still going to work fine. However, for the features, we have to note that this one can be more. We can even try something. Probably let's try to include precipitation because I also found precipitation. So let's try to include precipitation in the number of, in our new data frame, right? And so now you see, now we have precipitation. Now, let's check it. Oh, okay, it's an object, but it doesn't matter since we are not using it. We just want to, check something. So now we want to use precipitation. We want to use minimum temperature and precipitation to predict maximum temperature. So now we have two features, two predictors. And here we can now include that here. Because remember, our X is the predictor, right? And if you run this, and I should be running this below. I want to run it below so that. So now let us run our shape. You see now that it's now 119,040 by 2, and the target variable still remains the same because we just want to predict one output. So, and in this case, you can just say, okay, Y can be a vector and X can be a matrix. It doesn't matter, but just ensure that if you want to do any multiplication, just be careful about the dimension. And I would also advise you, I can also drop some links in WhatsApp. You have to probably, have good knowledge of metrics or algebra or something, at least metrics multiplication, this element-wise multiplication or, metrics multiplication, otherwise known as dot product or inner product. So, so what did we do? We talked about, how you can fit a straight line on some data. And, the idea is to minimize this distance, the average, error, the sum of square errors across all samples. And here was the formula. So we wrote an algorithm that we implemented. We initialized beta naught, beta 1. And in this case, you have to be careful. Beta 1 is beta 1 simply because you only have one, feature. If it were to be 2, then you would know that we would have another beta, let's say beta 2. So this beta 1 is strictly for the minimum temperature. If you have more than one feature, then the more feature you have. So every feature must have a weight, right? So beta 1 is the weight for the minimum temperature. If you have more than one feature, then let's say precipitation in this case, we would have like beta 2. So the beta 1 would be for the minimum temperature, the beta 2 would be for the precipitation. But because I shared this script and I didn't, so I'm going to remove it so that if you want to implement it, it remains the same. I can also just remove it. Yeah. So I think that was just, excuse me, that was just basically it. And I implemented this algorithm. Here we have our model, the linear model. And excuse me, please. Yeah, so I think everything is fine now. So we have this model. So we have this Y at, like I said, predicts this. It does this calculation, then outputs some Y at, and the Y at is just prediction. So we want to know how far is the prediction from the original value, right? And we just take the difference. We square it, average it, And then we do the backward. So it's what they call backward, you have the forward propagation and backward propagation. So just like the feedback mechanism I was talking about the last time, when you do something, you want to correct yourself, right? You want to know how far you are from the truth. And so what you usually want to do is you want to use this information of the original label as an added information for the feedback. It's just like you want to do something, you do the wrong thing, someone corrects you, you go back, you do that thing, again, you check, am I correct or wrong? It's just like that. It's just like, how can I say, it's just like for the first time you try to, you cook a food, you cook something, and you have never cooked that thing before. I can bet you that it's not going to be perfect, at least for the first time, right? And when you cook that thing, probably, you go to, you meet, I don't know, you meet someone, please just help me taste this food, or someone who is a professional in that, in that field, and the person tastes the food, and he or she says, okay, maybe the salt was too much, or maybe it's too spicy, or something, or the water is too much, and you take those corrections, into consideration, right? And the next time you will cook that food, you're going to use the corrections, as a way to guide yourself on how to, be better. And when you prepare the food the second time, okay, of course, probably it improves. You go back, taste the food. The person tastes the food. You say, wow, okay, today it's not too spicy, it's not too watery, but probably, it's too salty, or or maybe there are some ingredients that that are missing or something, and that person also takes that as a feedback, right? And goes back, and if the person tries, let's say for 10 times, 15, 20 times, then I can bet you that person would would make something very close to perfection. And I mean, that is just basically how the typical standard machine learning algorithm works. There is a forward thing, a backward thing. I mean, in case of supervised learning, in unsupervised learning, we don't have this feedback, remember, because there is no label. We don't even know the output. So we tend to use patterns, try to see if you can cluster, try to check the data that are somehow related, somehow, probably in maybe in terms of values or some properties or anything. Okay, and we wrote this algorithm, and this is the algorithm we are going to continue from today. Well, I'm not going to write the code from scratch like I did yesterday, but this is the same algorithm. And remember, in this place, we initialize the weight. This is the bias, right? And this is the weight. Remember, this is just one weight because we have one feature, which is the minimum temperature. Now, what did I do? I created a method to calculate the error, and it's very straightforward. Already, we have our data points, and the data points, already, they are the individual observations, right? And let me just explain to you. So what this means is, this is the first data point, and this is the second data point, third data point, fourth data point of the predictor, which is your X, and this is the first data point for the, the maximum temperature, what we want to predict. So we are using this information as an added, guide for correction. So as you can see here, so here we extracted the X, which is the predictor. Here we extracted the label. We need that label as an added information for the feedback, right? And the first thing we do is we will use this X, we just apply this formula, B1X plus B0, that is this formula, B1X plus B0. X is just the predictor, right? And when we are done, we want to know how far is the original label, that is the one from the original data, from the predicted one, which is what we just computed now, Y hat. This y hat here. Yeah. And this is the formula, y minus y hat square. That is just what is here. And this plus minus just means, we are summing it for all data points. Remember, we have about, if you remember yesterday, we had about 95,232 training data set, set. So what it means is that we are going to loop through all the 95,232 values. And we are going to be adding all the error because it's a sum, right? It's a sum. Look at it. It's a summation from the first data point to n. In this case, 95,232. You have to take the sum. Then we take the average, right? And what you see here is just the sum. And the average here is just the sum divided by the length of the point. So the length of the point, which is the 95,232. So here we just convert it to float because sometimes when you try to carry out operation on different data types, it might throw an error. So it's always better to keep it at the same type. And that's it. And for the update, we already have our error. We get the update. And the update is just, of course, here the forward pass. And we have the update. This is the gradient, which we calculated. So this is how much we are going to nudge, we want to nudge the parameters towards, that global minimum, right? We want to ensure that this loss here decreases as much as possible. As you can see from the diagram, we want to ensure that the distance, all the distance is minimal, right? We don't want, if it's too large, then our model is not learning anything. So, and when we get the gradient, we nudge it. We nudge it with this formula. It's a gradient descent formula. For accent, we are going to add, for accent, we'll do plus. This is very useful in case of probably when you want to maximize parameters, right? But in this case, we are not maximizing. Usually in machine learning, it's an optimization problem, and we want to minimize. Sometimes you can always maximize, but usually the goal is to minimize in most optimization problem. And that is why you see this negative, because we want to keep it down. We want to push it down towards that point where the loss will be very, very minimal, right? We want to ensure it's minimal. And we just do the update here. This formula here is exactly what you see here. Sorry, I'm just scrolling up and down. I wish I could, show the whole thing once. So here, beta 1 equals to beta 1 minus the learning rate times the gradient, what we calculated here, right? And that is what you see here. So beta 1 is equal to beta 1 minus the learning rate times the gradient. Same thing for the bias. And when we are done, you can see this beta naught, beta 1. This is where we are going to update it. So yeah, when we see. So, and in classes, there is something you have to note. This beta naught is an attribute of the linear regression class, right? It's an attribute. So anytime you call this beta naught anywhere within this class, it's going to overwrite this. It would always update. So just note that. It's just like you say A equal to 5, and somewhere you say A equal to A plus 5. Here, when you print A, you get 5. When you print A here, you get 10 because that A has been updated, right? So this beta naught, at the time we initialized it, once we update it here, it is going to overwrite. It's going to overwrite it. And the process continues. As you can see, it's an iterative scheme. It's an iterative process, number of iteration. We just do the same thing over and over, right? And if you notice, when we print out this was the B1 at the point of initialization, B1 and the B naught, right? And if you notice, as the iteration continues from 0 to 1,000, you notice that after the final iteration, after the 1,000 iteration, we just get this B naught and B1. So we are trying to adjust the parameter. We want that parameter that will give us the minimum I mean, that would minimize that, that error. And it's usually, based on this least square method. Also, someone asked that question too. I was able to answer. And, the idea of, gradient descent is what we are doing here. So, right, the step gradient is an iterative thing. And you can see it happens, at every iteration, But the standard least square method is just something that we use, and it's a closed form solution for, in particular, if you're working with very small dimensional space. But in high dimension, it's very difficult. Doesn't have closed solution. And we can just use this kind of methods to update. Yeah, and that was it. And we did it. We tried to test the model on the test set, and this was the something. And I'm going to send us another script. I mean, I will send another script later in this same problem. I'm not going to do that, but why I coded this thing from scratch is for us to know. Usually, you don't want to code all of this from scratch. There is a linear regression methods in sklearn, sklearn library. You can just pick it, put in your input, and that I will send the script in addition to this. I'm going to add it below. When I'm sending the script, then you will see that the result is more or less the same. I'm also going to add other machine learning algorithms like decision trees, random forest, and you can see how they perform also. Now, today, I just still use the same script, so we are going to start, today we are going to be talking about logistic regression. And unlike linear regression, logistic regression just focuses on predicting binary outcome, 0 or 1. It's as simple as that, a true or false. And we can just think about it as trying to classify objects or to classify things in two classes. Yes, and yeah, this is just for the purpose of just binary class. We just want to focus on binary class today. It could go more than, you can have more than two classes, right? And next week, when we go into deep learning and neural networks, we'll be going more than two classes. But today is just two classes. Simple logistic, just logistic regression. And how does logistic regression work? Logistic regression, the aim is to output probabilities, right? In linear regression, we output continuous values, right? In logistic regression, we want to output probabilities because, we are not always certain about the outcome of things. And it's always nice to work with probabilities because probabilities is also a good measure to tell how likely something would happen. Take for instance, if I tell you that it's going to rain tomorrow, it means I'm 100% certain. I mean, I'm sure that it would rain. Or if I say it's not going to rain tomorrow, then it means it's not going to rain. But it's very tricky because there are events that, they are quite uncertain, right? We cannot say we are exactly sure that this thing will happen. But if we model it, using this kind of probabilistic effect, then it could make more sense because it tells us how likely it happens. Now, if I try to, if I try to modify my statement and I say, okay, I'm 70% sure that it's going to rain tomorrow. Now it's different. I'm not 100% sure. It's just probabilities. Or I say, okay, I'm 80% sure it's not going to rain tomorrow. So now I'm now, scaling down my, I'm trying to make my statement not look exactly or, or it would never. I'm just putting my statement. So I'm just putting the statement, in a way that, the probability will tell you how likely it's going to happen. But if I say I'm 99% sure, then it's highly likely it's going to happen. If I say I'm 10% sure, then it's unlikely. if I say I'm 20% sure, well, doesn't look like. So, you know, you try to play around with probabilities, and you can see probabilities are just between zeros and one. You know, you cannot have probability that is greater than one. Otherwise, I don't think it's a probability already. So our probability is between zeros and one. So think about these objects. Let's say these are the data set, these green dots, right? And all these blue dot and the green dots. Yes, the blue dot and the green dot, they are the data points. Now, what I'm saying is that the probability that this guy belongs to, let's say a particular class, is zero, right? Or, you know, I say probability that, you know, this guy, let's say 0.5, right? And, you know, we kind of, you know, it's between 0 and 1. We kind of map it between 0, we kind of map it to 0 and 1. So, you know, here is kind of 1 or something, yeah, 1. So, and in this case, it could also mean, you know, when I say, okay, I have I'm maybe 90% sure, then it means I'm quite certain, you know, because it depends now on the threshold, because now you find this threshold, there's a threshold of 0.5. It means that if your probability is more than 0.5, then it's 1. Now, remember, I didn't just start with you know, how sure I am. I just started with probability. Then with the probability values, I can now assume, you know, here there is a threshold of 0.5. What it says is that if you have a probability greater than 0.5, then just take it as if it is 1, right? Or if you have a probability value that is lesser than 0.5, take it to be 0. Here, I think you also have some threshold values too. So you can okay, yes, 0. Yes, so you can see if you have y here to be 0.8, it's already more than the threshold value. If you have y here to be 0.3, you know, you already have 0 here, because the threshold is 0.3. So that means here, if you have a threshold of 0.3, it means anything above 0.3 will be regarded as 1, and anything lower than 0.3 will be regarded as 0. Now let's now go into in logistic regression, we want to predict an outcome 0 or 1, that is true or false, just like I just explained, based on one or more input features. So that is, we have some information we want to predict. The output of logistic regression is a probability that given that the given input belongs to a certain class. So we are saying that what is the probability that this thing belongs to this class? You know, just like I said, what is the probability that it's going to rain? Rain here is the class. So what is the probability that it would rain tomorrow? What is the probability that it would not rain tomorrow? So those are probabilities, and you can decide to, sometimes a bit tricky, you know, how you work with probabilities and also class labels. So you have to be very, very careful also. But today I will be focusing on, you know, the most basic things, which is binary classification. So, so that in order not to confuse you, I'm going to also explain. I've written the note down here in this notebook. Now, am I supposed to have included the sigmoid? Okay, yes. So now, how do we model logistic regression? Of course, for linear regression, it's straightforward. Sorry, I'll be going through the script also. We have this formula, right? And if you remember, the y-hat, the value of this y-hat, they are just real numbers. They are real numbers. They are just numbers between -infinity and infinity, right? They are real numbers. They are not probabilities. Remember, because our x is just, they are real numbers. Our x is just some real numbers. We have our weights also, they are just, you know, values, like, you know, they are just numbers also, real numbers. And this whole operation will just output real number. But in logistic regression, we don't want real numbers. That is it, we don't want real numbers. Remember, we want to output probabilities. We want to know the probability that this thing belongs to this class and this thing belongs to that class. Now, this is where sigmoid function comes in. Sigmoid function is a kind of, is an activation function, and it maps real numbers to probabilities. That's all. So it maps real numbers to, 0 and 1 probability number, values. And what does that mean? So what it means is that once I get this value, y hat, sorry, I'm switching because, it's very important for us to know the connection between, linear regression and logistics. I mean, they are not too far from each other, right? So when we do this calculation, already we know this. Now the question is, how can I convert this y hat to probabilities? That's the question, because I don't want to work with real numbers, because the problem doesn't want me to work with real numbers. And there is no way I can quantify that something belongs to, there's no way I can quantify the probability that something belongs to a class if I don't have a probability value. So the question is, I have to convert this y hat, the result, to probabilities. And how do I do that? The sigmoid function helps to do that. So the sigmoid function is also a family of, activation functions, and this is just a special case. And if you're very familiar with statistics, you see this is just not far from the, kind of, this is like this formula models, logistic, growth, like, population of something that, that has, carrying capacity of something. And what it means is that, sorry, it's not clear, but this is Z. So now, please just follow me. Now, what this Z means here now is that, so first of all, forget about the Z. What does this curve say? Now, yeah, sorry, I could have, but just this minus 10 to 10, yeah, please. These are the real number line. This line, the x-axis, the real number line. And it takes number between minus infinity to positive infinity. This is just minus 10 and plus 10, just, for us to see, just for, for visuals, for better visuals. I don't want the numbers to be too big or too small. So, but just think about this number on this x-axis is what the linear regression would output, because it would output real numbers. And you know what real numbers, we know what real numbers means. So they are just numbers that, just any numbers, any type of numbers, they are just, at the very top of the number line, and they can take values between minus infinity to positive infinity. Those are just real numbers. And, real numbers can be anything. They can take any form. If you're very familiar with your real numbers, they can take any form. When we talk about usually any number, regardless of the form, we talk about real numbers. And so if my linear regression model, which is this formula, y hat, in this case, we have been using y hat, right? Because that is the end result. Usually we use y hat as the prediction, right? But remember, this y hat is not the complete prediction in terms of logistic regression, right? Because we still need to convert that number to probabilities. That is the idea. So what we want to do is that we might not represent this with y hat. We can say, okay, let this be z. In this case, like, sorry, I can just type by the side of my screen. I can say, let it be z. So instead of, it will be b1x, right? Plus b0. So what I've done here is just, I don't want to use y0 because y hat is not the end, result. I still need to convert this z now to probability, which will now be my y hat, right? So somehow I have to convert my z, to probability. And how you convert it is using the sigmoid function. So this sigmoid function here, you will feed the z, that is the output now of this linear regression, this linear operation. We feed it into the sigmoid function. And what is the function? This function here. This is the function. 1 divided by 1 divided by 1 plus exponential minus z. Remember, what is the z? If you look down here on my screen, you will see that z is nothing but this linear operation here. I don't even need to switch again because it's very clear, right? I think we are seeing. So this z now is now the result of that linear, that linear operation, right? And once we feed it into this function, it looks like this, because now what you see here is just that linear operation. We take the exponent. We take the exponent of that value, which is a real number. Then we just do this operation. Our y hat, which is what we want, becomes now a probability between 0 and 1. As you can see, the sigmoid function maps real numbers to 0 and 1. That is, the minus, if your real number is minus infinity, your y hat will be so close to 0, as you can see from this curve. Then as the number begins to increase up to positive infinity, the probability starts to move to 1. So the higher the number, the more likely the probability. That's just what it means, because now we are working with probabilities. So, and when sigmoid function maps these numbers, it tries to, shrink, the numbers into, between 0 and 1. And what sigmoid will do is that it will ensure that if the model outputs very large number, it will give high preference probabilities to that number. So that is the job of sigmoid function. Sigmoid function is just an activation function that maps real numbers to zeros and 1. And as you can see it here, it maps all real valid numbers into the range of 0 and 1, which can be interpreted as probabilities, at least in this case, because that is what we want. We want probabilities. Now, I would proceed. So already, the y hat, remember, it is zeros or 1. Remember. And now there is something I also want to say. So, when we say y hat, that means, we want to actually, we want to predict the class. For example, you want to, you have 2 classes, right? The first, I can just type, so for easy communication. So you have 2 classes, like in the data set we are going to use, I'll talk about it, but let's just say you have fruits. Let's say you have 2 fruits. The first fruit, let me use orange. Okay, yeah, 2 fruit classes, right? Let's say the first class is mango, and the second class is orange. Let's say, I think it's better. Let me use color. Let me use color to color. Yeah, let's say red and black. So let's say you have objects and you want to group this object according to class their colors. Let's say the objects can only be red or black. And then you can say, okay, let me assign color red to 0. And let me assign color black to 1, right? Now, in this case, you can think about this. In the case of binary setting, you can think about these 2 numbers as probabilities. Yes. And the closer it is to 0, the more likely that it's going to be red. The closer it is to 1, it is more likely that it's going to be black. So that's just the whole idea. And why it is like this, because of this setting, we are in more binary setting. And since the sigmoid function always outputs 0 and 1, then we can just, say that, okay, if the probability value is closer to 0, then I can just, assume that the color is red. So that is what it's trying to say here. For example, y hat is the value we are trying to predict. And remember, in logistic regression, that y hat is the probability. So we are trying to predict the probability of class 1, or let's say class 0. It could be anything, right? And remember, our x is still the same. Our x are the features, the input features. The beta 1 doesn't change. Already we know beta 1 is the weight corresponding to the input features. And the beta naught, the bias term, is just similar to y-intercept in the linear regression, which is what you know. Now, I'm still going to talk about this x particularly because all along we have always, I've always mentioned that x, x is just the values, which are the features, could be the data point. But well, in the last example, we worked with just one feature, so it doesn't really say much because it's just one feature. So you don't need to think about kind of metrics things or matrix multiplication or thereabout. But when we are working with more than one feature, we want to do a kind of vector multiplication, kind of matrix multiplication, because now we have x. X will now be in form of matrices. And I talked about that here when I printed out the this result, because now we have something that looks like a matrix, 119,040 by 2, right? And we don't want to start looping through the features and multiplying each by their weight. So there are more efficient way to do this kind of multiplication. And if you're very familiar, those that are familiar with metrics, they know what it means. If you want to multiply, things that multiply matrices. But I'll talk about that also. So now let's proceed. Now remember, our y hat spits out a probability between 0 and 1. So the question is, what is the threshold? How do I know that this belongs to this class or this belongs to the other class? Now, in our illustration of the color red and black, because the probability is between 0 and 1, let's say 0.3. Now, let's say the y hat is 0.3, right? And now the question is, where does this belong? Like what for this particular example, for this data point, which class would I say it belongs to, red or black? So that's also one of the things that that's very in problem statements. You have to understand how to your threshold, and that threshold is very important because that is what that is the value that you would use to classify that example, that observation or that data point. Now I can say, okay, if I want it to be that I want to use a threshold of let's say of 0.5. What it means is that if my y hat is more than this threshold, if my y hat is 0.5 or more, then assign it to class 1. Otherwise, 0. Now, in this case, because of this y naught, 0.3 is not up to that threshold of 0.5. This automatically becomes what? Class 0, right? This is just one case. Now, let's go to another scenario. Let's say the model spits out y hat equals to 0.7. Now, in the comment section, can you type this the class this particular data example would belong to? Just in the comment section so that I will know if you are following. So which class because the threshold is 0.5. Remember? Threshold, yes, 1. Thank you. So now it belongs to class 1. Now, so this threshold is a very important metric or the kind of value you want to use, because the probabilities are just between 0 and 1. So you have to decide You have to decide, where someone else can say, okay, I want my treasury to be 0.7. So, what it means is that if you have, let's say, if you have another case, if I change the metrics now to 0.7, let's say my y-hat now is 0.6. In the comment section, can you tell me where this particular example will fall into? The threshold is now 0.7. Remember, threshold is 0. Yes, class 0. Thank you. So the threshold tells us which class that example would fall into. Now this would be 0. Okay, that's just it. Runtime, okay, because I'm not using. So now this is just by the way, you can see, but as a custom, the people always go with 0.5, which is the inbuilt, thing, because if you look at it, it makes sense, at least in terms of, yeah, I can just say naively, we just want to say, okay, if something is 0.5 or more, let's just assume. Well, it might not be the case. There are scenarios where you really want to be sure, because sometimes 0.5 is not completely sure. Because when you say 0.5, 0.5 means 50%. And you know what 50% means? It means maybe, maybe not. In medical settings where, where you have to make a decision that might be very costly, you have to be very sure. You can say, please, I want to keep the threshold at 0.7. What it means is that if it's not more than 70%, please, I don't want to assume that this probability, this thing would belong to this particular class, right? And it's always very important for you to know. Now, let's go to our data set. The data set is what my colleague talked about last week, that breast cancer data set, right? And it's an inbuilt data set. It has 569 examples, that is 569 rows. It has 30 attributes, that is columns. They're all numeric, right? And they have all the attribute information you can find. The label is a binary variable where 0 means benign tumor and 1 means malignant tumor. Just to be very clear, these are tumors where there are tumors that can be cancerous. There are tumors that are, but in this case, benign tumor are not cancerous, right? They can just that area can look like, it's not cancerous. That is, it doesn't grow the way, like it's not harmful or something like that. Something like that. So I think those in the medical field can confirm this, that malignant tumor, not all tumors are cancerous. There are some that are just probably due to some kind of disorder or something. And those kind of tumors, they can just cut them off, operate on them, and it's not really health. It doesn't pose a threat or something. But malignant tumor is cancerous. And the question is, can we predict whether a breast mass is malignant, that is cancerous, or benign tumor, which is not cancerous, based on the recorded attributes? Each patient, they have these attributes, right? And remember last week, my colleague, talked about this data set very, I also followed the class, and I think it really said a lot of things. So today I won't say too much, but I will just take a glance and go straight into our model. Now we load the breast cancer, and we can, and mind you, if you're working with methods in Python, it's always good for you to know what attributes what are the attributes of this method. Now, when we load this cancer, data set, if you try to print cancer, it will just bring out some kind of, a lot of things, like you can see, cancer. However, there could still be some added information. If you scroll through, it looks like something that still, that can have some information, because data.describe means something. So usually what you want to do is to use there's this dir, I think, tells us, the attribute, or if it's a class object, it can easily print out, some of the attributes of that method or class method or something. So, and that is why you see this .descr. It's not magic. It's just here. So this would describe the data. This one would extract the data. If you put it here now, it will just extract the data. You can see just the data. Strictly the data. This one, feature names, would print out only the features. That is the variables we want to use. You can see mean radius. They are playing, I think they're up to 30. You can even check, you can confirm the length of this, the length is 30, as you can see. Now, what else? Let's check the file name. What is the file name? breastcancer.csv. What is the target? The target is, zeros and one. Remember, in logistic regression, we don't work with continuous values. You can see these are classes, 0 and 1. 0 here means this benign tumor, and the 1 means malignant tumor. Now, what are the target names? Because this number, zeros and 1, what does it mean? We don't even know. So some added information. You can see. So that is it. And you can also read about the data set, so that you can be sure that you are well, you are well grounded, because you need to understand also the data set. This could be any data set, right? It could be any data set. And as you can see, it's you can use the describe, function here to, it explains the data, it tells us the radius, the mean of the distance from the center to the point. These are just some medical things, and you can read about them. As you can see, it also tells us the mean and the maximum values of each of these parameters, each of these columns. And we have the class distribution to be, we have 202 malignant, examples, and we have 357 benign, tumor examples. So yeah, you can read about these things, nothing much. Now let's just, let's try to view, well, I was not interested in putting this thing into data frame, because sometimes we can just extract our data and just start to work. But I just, work with this so that we can see, this just converted into data frame, right? And this is a concat kind of column concatenation. So, we have this cancer, because this cancer here, if you look at when we print, sorry, I go up. Okay, here, let me just print what you have. So you can see, we just have a lot of things, we have data, this is a dictionary, right? This is a dictionary. So we have data, this is the key, these are the values. We also have targets, the keys, the values. We also have some things, frame is none, target names, they are just arrays of blah, blah, blah. And yeah, this is a dictionary, not a class of it, sorry. And now we just, try to form a data frame from there. So we extract the data, which are the values and the target, right? And the columns, we just try to, name the columns because there's a feature name. Remember when we printed this, this dir directory, something, we found this feature. And, so what it's going to do is it's just going to stack this, by column, and get this data frame. Now, these are the variables we want to use. We want to use all these variables to predict the target variable. We want to predict the target variable. Now, let's proceed. Let us just plot some things. Let's just play around with our data frame. I just here wanted to plot, the target variable against the, one of the features, which is the mean radius, right? So when we plot it, you see how it is. So this is quite interesting. You see 0 or 1. So now you can see it's not a continuous number that looks like maybe a kind of scattered plot. Its idea is 1 or 0. And from this graph, it looks like to me that, patient with a smaller mean radius, are likely to, I mean, like from this example, because this is the mean radius at the x-axis, you can see, and somehow, if we go along this x-axis, we see that patients with smaller or let's say lower mean radius are likely to fall into this class of malignant tumor. And as you can see, as the mean radius expands, then well, I think this is quite tricky. I think okay, let us read the mean radius properly. I think I misread something. It looks to me that the 0 should be for the, it's just a moment, mean of the distance from the center to the perimeter. The mean standard. Okay, malignant, I'm thinking. Yeah. Yeah, it's not completely clear because there's nowhere it was explicitly, stated. But I tried to Google the because I wanted to be sure about the labels. But I found out that this 0 is for just like I said here. 0 is for benign tumor and 1 is for malignant tumor. However, this might be subjective, but the goal is just to ensure that the model is able to classify these examples correctly. But if you can also do your research to be sure. And I was a bit skeptical when I tried to print the targets. Yeah, that was where I was somehow skeptical of, okay, no, it's the target names. That's also. Yeah, usually this is the label, this is target names. And if we look at the index looks to me like 0 is the malignant tumor and the 1 is the benign tumor. So probably I have to change this from what I understand. Yeah, the index of because if you look at this, the index also, of course, in this binary case, it might mean that, it's a malignant or not, but that's the problem statement we would find out later. But for now, whether it's 0 belongs to this class or 1 belongs to this class, it's just a matter of which of the classes, whether it is malignant tumor or malignant tumor. But it wasn't explicitly stated here in this data. But eventually we would understand what it means. But according to from what I see here, it looks to me like, if we have a kind of tumor, okay, I think it might be wrong though, because both benign and malignant tumor are just tumors, but one can be cancerous or not. Since I'm not a medical practitioner, it might be difficult for me to know the exact features that might actually, but just for us to know what the interpretation of this graph just tells us that it's likely that the patient with, lower mean radius are more likely to fall in this class, and patient, with the higher mean radius are likely to fall in this class. So that's just it. So we also, describe the data set, and, we see some kind of count, the mean, the standard deviation, minimum 6, here is 9, maximum here is 28, here is 39, here is 188, here is even 2,501. So if you look at this data description, and you want to use these features, because these features are very, very important, because they are features that have been medically tested, that these features can actually tell us if a patient falls into the class of benign or malignant tumor. So in particular, when you look at your data, you always want to know, how is your data scaled? Because this data doesn't look like it is scaled, they are scaled, I mean, they don't have the same scale, because the minimum of this is 6. The minimum of this one is 143. The maximum of this is 28. The maximum of this is 2,501. That's too much. The minimum of this, look at this, is just 0. and the maximum is 0.2. So as you can see, they have different scales, different, minimum, maximum. How do we bring them together? Like we want to, we want to ensure that they are in the same scale, because if one feature has very high scale and the other one has very small scale, very low scale, the model is not going to learn very well. It's going to take longer time, for the model to convert. This is because it's trying to jump, because along one axis, the scale is very big. Along one axis, the scale is very small. During the gradient descent, it's not going to properly, explore this, space, of trying to find the kind of global minimum. So what it does is it kind of create this kind of weird, Google Colab. Okay, I saw a question. I'm having error when, okay, I'm sorry, probably because maybe I changed something, but I didn't share this script though, because I think I shared this yesterday, but if it's giving error, I can address that. So back to the issue of scaling. If you look at this data set, they are scaled differently. For example, the minimum of this is 0.05, maximum of this is 0.2. And we have one, in fact, look at this. This is even 4,000. Now, what we want to do is to scale. First of all, before scaling, let us extract our X and Y, right? That is what we want. Remember, our X now will be our feature, and our Y will be our target. Remember the cancer data set. Remember the here we have the data which gives us the data just basically gives us the each of the values of the columns, right? And the target just is the remember, this is just the target. So we want all of the features and all of the targets, because we need both to train our model. X is the feature and Y is the target. And this target is, remember, is the binary class, right? And let us print out the the shape. We see that it is 569 by 30. And the Y here is 569. Well, in this form, it's just, this is just, like I said, usually the labels in, in mutually exclusive, events like this, we just have, regardless of the number of features, they just belong to one class. We cannot have one patient that is both benign and malignant cancer, something like that. Yeah, so I always find it very hard to pronounce those things. But yeah, but just think about that. So for the first example, let me explain what it means. So let me explain. So let's take the first training example. Remember, Python index starts from 0. Now you find these numbers. So this is for the first patient. And this will be 30 in number, because that is the number of features you can see. And you can check. Or rather, we can just use .shape. Is it 20? Yeah, so you can see we just have 30, because this is for the first sample. For the second sample, it's also 30. So you can see. So up to 569, that is why you see 569 by 30. Now for the label, we just find 1, because, there is no shape, sorry, because it's just one number. So there is no shape here. But in this case, we don't care, because they can only belong to one class, right? And we don't want to add extra dimension or something. So yeah, so that's just it. And just like if I print the number, you just see it's just 0 or 1. So you can see this is the This is the first sample. This is the second sample. The third sample. Oh, they're all zeros at this point. Okay, let me just print the first 20. Okay, these are the first 20 samples. You can see they're just 20. But for the X, if I print this, it's going to be 20 by whatever, 20 by 30, because each of the samples have 30, features. Now, let us proceed. Remember, I talked about scaling, the scale of our data. These scales here are not properly scaled. The numbers are just kind of jumping, and we want to scale them. And usually, what we want to do is to normalize. We want to normalize the data. We want to center the data around their mean. So what it means is that I'm going to take the mean of each of the variables and scale them. Scale them, and you know what that means. We scale them to their scale them around their mean. We scale them around, like just using a standard Gaussian, right? So what it means is that we take the mean and we scaled it. So with mean 0 centered around mean 0 and standard deviation of, depending on the standard deviation of the data. But usually what we want to do is we want to center this data. We want all of the data to be centered around this, this standard Gaussian. And we can just do that by, it's very easy. We have our X. Our X here is the data set. And you can see now, we take the mean. Remember, we take the mean. And this mean here is along the, columns. So like that is each of these columns here, each of them. So it's going to start with mean radius, take the mean of only this mean radius, then center each of the points around this mean. And I think if you are very well familiar with statistics, I think it's just a kind of want to scale some kind of, you have some mu, and you want to scale it with some sigma or something. So what you do is that when you find your mean and you find your mu, which is your mean, then you now subtract your points. You subtract the mean from the points, right? And such that any values that is closer to the mean would just be 0. Which ensures that we are not only just trying to center our data around their mean, but we want to standardize it. We want to center it around 0. Now that is, by the way, we are done. Now let us print out our first data set. You see that it has been rescaled. If you look at this data, initially there was no negative values. Now you can see some negative values, because at the end of the day, we have values that are less than this mean. And I think I can even try to plot. Let's try to plot let's try to plot one of the columns. So yeah, let's try to plot one of the columns. So you can see, yeah, so this is one of the columns. I think this should be the first column, which is which should be, let's say, mean texture. Yeah, mean texture. Yeah, mean texture. So initially, this mean texture, if you notice the values, the minimum is 9 and the maximum is 39. Now, if you come to this histogram now, you see now that it's kind of centered around 0, right? And you can see. So if you look at, if we check this for all the data points, you will find out that all of them will be centered around their mean, as you can see, 0. Let's check for the second one. You can see. So if you do it like that, so now they are properly scaled, right? They are properly scaled. That is what we want. Now let us split our data set. Remember yesterday I talked about, you want to train your data set and you want to test it on unseen data. So usually we use this train test split. It's also a method from the sklearn library. And what you want to do is just remember our X and Y is the complete data. Remember what we did here. Remember, it's just the complete data of 569 by 30. But of course, we don't want to train the model with 569 because how do we know the performance of our model? So let's use a test set. This is what we are going to use to test the model. We want to use 20%, and just kind of put a kind of random state. This would ensure that if you continue to run this code, split it, you have the same split. So now let's split it. Now let us now print our shapes. Sorry, I'm going to just Y test. So this is for the test, then Y train. So let us print it and let's see. Now you see, remember our data set before, the complete data set was 569. Because we have taken 20% out, we are left with 455. So we are going to train our model with 455 training examples, each with 30 features. This is the label of the training set. This is our test set. This is what we'll test the model on. This is the label of the test set. Now let's jump into our algorithm, just like sorry. I think I don't know how this, probably I could have just taken this out. Sorry. Okay, yes, so this is the logistic regression algorithm. And if you look at this algorithm, it's just exactly as yesterday, but some things will change a little. And this is because, remember, I talked about this, because we are not working with, real numbers. We want it as probabilities. So we would first calculate this linear, operation. And then we would just, feed these values, the real values, into this sigmoid function. And the y hat will be probability. That one is clear. As you can see, x and y hat are the predictor and predicted, right? So the s are the features, and the y hat is the, probability. Now for the cost function, remember yesterday we used mean square error. In probabilities, we cannot use mean square error. That would not help to penalize the loss. Yes, and this is because we are working with probabilities. I put a link here to see the proof of this gradient, but I would also put more materials. But this function is what you see here is a binary cross entropy. It's a binary cross entropy, and it's if you also are familiar with your statistics, you find out that this is just this is the Bernoulli. It's just the logarithm of the Bernoulli distribution. Bernoulli distribution is is a discrete there's a discrete probability distribution that that kind of that outputs that kind of outputs that tells us if your experiment, whether your experiment is a success or a failure or something. So it's just like you throw a coin, it's head or a tail. It's just a special case of the binomial distribution in just one trial. We just want to know, okay, if I do this experiment once, what am I going to get? So what is the probability that I'm going to get, given that it's conditioned on on this class, something like this. And yeah, this is the loss function. And why we have this negative here? Normally, the Bernoulli something, you always have kind of y hat raised to power y plus y minus I, y hat raised to power 1 minus y. So, and because we want to minimize, remember in the optimization problem is we want to minimize, we don't want to maximize. So you add the negative and the negative. And when you take the derivative, when of course, you know, we want to get the loss across all the training examples, not just one sample. This one is just for one sample. And this is what you see here. But remember, we have, in this case now, we have 455 samples. So what it means is that we have yi. Your I is from 1 to 455. So we have to take the average, remember? And we do the same thing too, the gradient, you know, the backward. Remember, we want to update the weight. And if you differentiate this, cost function here, you get this. I put the link here. I'm still going to, you know, add some more links to this slide and I share. Here you see the link of how they differentiated this with respect to beta naught and beta 1. And they got this. And remember, we are very familiar with this formula. It's the update formula. Nothing more, it's just the same. And that's all, we just repeat. Yes, I think I also, I also extensively explained, you know, how from the Bernoulli distribution, how we derive the loss function for the logistic regression. So I put it here in the slide. You can see, we started from here, probability mass function. And then we arrive at this place, which is already what I showed. But for the purpose for time, I'm not going to explain, but I promise you, I will put a link and you will just understand everything. But for now, I just want us to focus on the algorithm. You know, nothing changed actually. And this is what you always see most times, you know, in supervised learning problems. You know, you have some kind of forward pass, get some kind of, you know, updates. You want to get a loss, you kind of do a kind of gradient, you know, descent, and that's all. And you do it iteratively. Okay, yes. So yeah, I also showed the log. I also showed why we always use the log. You understand? Usually, why do we use log? So we use log, yeah, probably because, you know, it is computationally simple, and, you know, also for numerical stability. You know, so most times we always want to use log, right? And in like I said, in optimization problem, we want to work with we want to minimize. We don't want to maximize, and that is why you see here. I explained to you why we have this negative. You know, for the loss, why we have the negative here. Normally, this is the standard formula. This is what you would always see, you know, in a standard Bernoulli formula. And in fact, you would even see it here. If you take the logarithm of this, you just, because this is a product, you have plus. But you find out that here is, you find out here that it's minus eventually. Why? Because we don't want to maximize. We want to minimize. We want to push it down, right? And this is just something that can also explain. So you have the logarithm, as you can see, you want to maximize. Your x values, remember, the values in the x-axis is what your model spits out, right? And it's between 0 and 1. But if you look at this likelihood, when the value is small, we have the loss to be small. When the value is big, when the probability is close to 0, you know, we have, like, you know, kind of, you know, we find the error to be small. When the probability is closer to 1, we find the error to be big. But we don't want that. We want to ensure that when the probability is close to 1, the error should be small. We want to minimize, and that is why we just take the negative log. And you see that this is just the inverse of this. So what it means now is that if my probability is close to 0, I will be having a very big loss. I mean, I'm focusing now on if what I'm actually predicting is 1. So if I want to, you know, if the class I'm predicting is actually, you know, 1, closer to 1, that is the you know, the correct thing. Eventually, that is what we want. You know, we want to ensure that, you know, we want to predict the right thing. And when the probability is closer to 1, you see that the loss function is very minimal. Although, yeah, you also find this, you know, in normal cross entropy, you know, but also in terms of this binary cross entropy, you know, it's kind of similar, because in the end, the Bernoulli distribution is mutually exclusive. That is something as, so this is one term, and this is another term. So if my yi is 0, you find out that this term just vanishes here. Here would be 0. Here I just have 1. right? And I'm just, I'm just, here 0, here would go, here would be 1, and I'm just 1 minus 0. So what it means is that if the prediction is closer to 0, I should be getting also something very close to 1. And what it means is that eventually I'm here and I will have a decreased loss. Now, what if what if I'm trying to predict class 1, the probability that is closer to for the class 1, right? So if yi is 1, this time just vanishes here. This one disappears. And I have 1 here. And what I just have is just log whatever I get. So the idea now is this probability also should be closer to 1, right? Yeah, and that's just it, because that is the original label. And eventually I'm still here. So they are mutually exclusive, right? So I can also send videos so that we can also understand how this works. But let's come to our algorithm. The algorithm is exactly as I did yesterday, but there were some modifications. So why I didn't try to write from scratch today is because of time. And now look at this guy. Now look at this guy. So they are the same, but something changed. Now remember when we were writing yesterday's code, because we were working with only one feature, we just explicitly just initialize the weight for one feature. But this would fail when you have more than one feature, because I'm only initializing one feature. But in this case, in our problem now, we have 30 features. Remember, we have 30 features. So you can, instead of just like writing self.b1, self.b2, self.b3, self.b4 up to b30, it doesn't make sense. So we can just randomly initialize 30 samples. And I think I can even run this. I can run this above here so that we'll see. So let's say yes, 30. So when, oh, sorry, I'm not supposed to do this. So let me print the shape. Let me print the shape now so that you will see. So you can see now, what I have now is 30. It means I've initialized 30 weight. And that is why when I print it, you see 30 numbers here. These 30 weights now, remember we have 30 features. And I explained to you the last time that each feature will have its own weight. This one will be for the first feature. This one will be for the second feature. This one will be for the third feature, up to 30, right? So this is what this initialization would do. And we would only have one bias. Yes, this is because, for every, because we just have one output node. It's just one node. So, and it's just on one single expression. If you look at this formula, let's go back to the formula. You see here that, this X here now is like 30 now. Remember, it's like now it's not like, sorry. Our beta 1 now is 30, right? And regardless of the number of X, because here we have 30, like examples by features, and here we have some kind of vector of weight. Here would still be 1. We must still use one bias. So that's what it is. So it doesn't matter. So we still have our one bias, which I defined here. Now, our sigmoid, remember our sigmoid function, right? And if you followed also, this is the formula for the sigmoid function. Yeah, sorry, I'm moving up and down. I think it's very important for us to, oh, did I skip it? Okay, yeah, this is it. So 1 over 1 plus exponential of minus z. It could be anything, right? So it just depends on what is coming in as an input. In this case, I can say z, I can say x, doesn't matter. It's just the output of the linear operator, which we know. So in the code, what I did was to, that's just it, 1 plus exponential. In fact, I can even use z so that I don't want to change notation, so that we would know that yes, this z is what is coming in from the linear operator. Remember, and the error. Now remember the error. I also remember this is the error, right? This is the error for the logistic regression, and this is just what you have here. I mean, it's just the direct implementation. So we have y times y at plus 1 minus y times log 1 minus y hat. And that is exactly what you see here. Y times log y hat plus 1 minus y times log 1 minus y hat. So that is what you see here. And here I added this clipping so that to ensure numerical stability, it's always because logarithm is a very, can be a very silly, logarithm is something that if you're not careful, you can run into problems, especially when you are, because there are points in the logarithm scale, or in the log function, log 0 is undefined. So we don't want that. So we don't want our y hat to be 0. We don't want it. Or we don't want it to be extremely, extremely big. And then there's a problem, right? So we want to keep it, we want to clip it, just like you are clipping. So we want to ensure that, they are just strictly between 0 and 1. So, but it's optional though. If I run into problems, I would uncomment it. That was why I put it there. But usually it's the case that you want to clip it to ensure numerical stability. And you just return the error. Now the step gradient, remember, we also did this yesterday, right? Everything I'm doing now is we did it yesterday. You can see it, step gradient. But the implementation will be different, remember, because now we are working with with logarithms, and you can see when we predict our x, and remember, okay, okay, the predict is down. Sorry, I should have kept the predict up so that for us to see. Let me put it up here. Well, it doesn't matter anyway. So the predict now, remember our sigmoid. Remember that when we calculate this guy here, sorry, I think I can just, I want it to be as I explained. So this is our z, and we just put the z. This one is the linear, is the linear operation. Remember, for the normal linear regression, we have so in this case now, I'm taking a matrix multiplication plus our bias. And this is because if you look at this formula very well, our x now is not just a number, it's not just one data point. It's, because, for example, it's, we have it to be 455 by 30. Yeah, this is it. You can see 455 by 30, right? So, and, our B1 is not just B1, it's just B. And the B is, it has 30, it has 30 features, right? It has 30 weight. It's a vector of 30, something. So when you do the dot product of this, and so let's say this should be like, let's say 1 by 30 or something. Yeah, because it's just a vector or something. So now what we want to do is to do the dot product of this, it has to be a matrix multiplication. So something like, and matrix multiplication, the dimension has to be consistent. So we would have something like 1 time, we would have something like 4. So just look at this, in this code here. It depends on how you code it anyway. I don't want to do any transpose here. But what it means is that if I take this dimension for x times my vector, my weight vector times 30, let's say by 1 or something, then what am I going to get? I'm going to get 455 by 1. Or even though there's no additional, dimension here, because, you will get something like this eventually in your output. So this 455 now is the output probability. In this case, it's just z now, is the, eventually. So if it is z now, this is just the output value is the output of that linear operation for all the 455 sample. We just do it one. It's called a kind of vector multiplication or vectorization or something. Yeah, so because it's efficient, we don't want to look through all of these features one at a time and multiply with the weight. We can just do it on the fly. And this is what the dot product will do. Yes. And when we are done, because we don't want real numbers, we want probabilities, we just put it into the sigmoid function. This is our sigmoid function. So this Z now, we just come here and it will enter into this place and it will perform this operation and it outputs probability. This one is probability, right? And so quickly, now we compute the error. Already I've explained that. And we do the step gradient. Remember the step gradient for our update. Remember, it's a straightforward formula. This formula is straightforward. Already, now because we also do it in a vectorized form. We don't want to be calculating each gradient as we did yesterday. If you look at this point, we calculated B0 gradient, B1 gradient because it's just one weight and one bias. But in this case, we have 30 weights, which is self.b, and one bias. So we can just also do it in the linearized form. And as you can see, we find the grade, for the gradient, for only the weight, we would already is here. This is the formula we are applying. Sorry, yeah. This is what we are applying here. You can see. So yes, and there is something you have to notice. I transpose this because quickly I have to also explain the problem of transpose, because sometimes when you're working with metrics, I think it's always very tricky also. Now, why did I transpose it? If you look at this y hat minus y, what you have here is just n, nothing more. Is the number of because it's the output probabilities, right? And you just subtract it from the from the ground truth. But if you look at the formula here, we have to multiply. Sorry, here we have to multiply x times this, x times this. This is n. Your x here is a matrix, right? And you know that matrix is of dimension 455 by n. You cannot multiply these two like this. How can I say? Yes. So if x would come first, or depends on how you multiply it. And what I did here was, so this is how okay, sorry, this is not by 30. Yeah, so my n is here, yes. Because the n is the number of examples. Please note, in this case, it's 455. Let me just write it explicitly, 455. Now, what you see here, y hat minus y hat, this is what you are going to get. But your x is 455 by 30. If you cannot perform matrix operation like this, if you are very familiar with matrix algebra, for two metrics to multiply, the second dimension of the first matrix and the first dimension of the second matrix, they have to be the same. So what it means is that I have to flip this one to 455. And then when I multiply by 455, what I'm going to have is 30, which is just, the gradient of each of these 30 weights, right? The gradient of the 30 weights. And from this point to this point is why I use this transpose s dot t. Once you put s dot t, it's going to transpose the dimension. So that matrix multiplication will be possible. And yeah, I just did this for B0, and we train exactly what I did yesterday. I didn't do much. Let's run it. I will talk about this accuracy or something in a minute. So we initialize our model, remember, and now number of features is an additional input to our class, because this model can work for any arbitrary number of classes. If I want to use features rather, not classes. If I want to use 4 or 5 features for my prediction, I just make sure that I use 5. If I want to use 10, in this case, our x dot shape, it will just give you the shape of the matrix, right, of the training example. But we need this 30 because that's the number of features. And Python index starts from 0. So this is index 0, this is index 1. So when you put 1 here, you get your 30. Of course, I can just easily add code it, like I can just put 30 here, but I think it's not always good so that you don't have to be changing the numbers all the time. You can decide to work with just 6 features and then it's just fine. Okay, so now let's run our model, model.fit. You can see very fast. Now, these are the weights at the point of initialization, that is your B1 to B30. I mean, sorry, yes, that's your B1 to B30. That's our weight, remember, and this B0 is the bias. So this is the error at the point of initialization. But after 1,000 iterations, we notice that the error, you can see the error is dropping. You can see, so this is the feedback mechanism. And this is simply because of this update here. So as the weights of the model are adjusting, the error will be reducing because the model is learning. If your error is not dropping, sorry, it's not learning. Go back, right? And at the end of the day, we find out that our model is not, I mean, these are the finalized weight. You can see what we started with is not what we ended with. This is because at the point of initialization, it's just random guess. But when we start this backward, gradient update, then the model starts to learn. And you can see the error at the start was 1.54. The error now is 0.1. And that is the objective. We want to optimize by minimizing the loss. That's the idea. That's the whole idea. We want to minimize the loss. Okay, someone said using start model library, can we use log regression? Yes, of course, you can use log regression. You can, I mean, there are regression models in sklearn. For me, I was really not interested in, in just calling libraries. Why am I doing this? Because for some of you that want to go into more advanced, data science program, like you want to do NLP, or you want to go into computer vision, right? You want to do things that are really advanced. I can promise you, you would write complicated, complex codes, and you really want to structure your codes in a way that, you can actually interpret. Well, you can also use libraries, but at some point, you still have to write codes. You are not going to be using libraries all the time. You are still going to write codes. And the goal of this, of this section, of this, training is to train you guys, okay? Like to understand how algorithm works. Because look at how I started from simple algorithm here, to the implementation. That's just exactly, what you find in libraries, right? Yeah, there is no number of maximum iteration. For example, let's check. If you look at our error from 1 to 5, we notice it was dropping. So it means I can even increase the iteration because it looks like it can still, the error can still go down more. You can see it's even reducing. Wow, that's interesting. So I just wanted to, I think let me reduce this to 500. I don't want to see too many print statements. So here, let me use 5,000. At every 500, 500 is still too much. Let me use 1,000. So that here my iteration is 5,000. Okay, I can even increase it to 10,000. So I can only just see 10 iteration. Yeah. Wow, what did I do? Is it 100? Wait. Oh, this is 10,000, right? Oh, I'm surprised. Why is it bringing out? Oh, this is this every 1,000? No, this doesn't look like. Wow, it's printing out every on. Oh, I didn't run the code when I didn't update the script. Okay, yes. So now we see, yeah. Oh my God, it's still doing the same thing. For I in range number of iterations. I'm so sorry. This is 10,000, and this is 1,000. Okay. I only ran this something here, but I didn't initialize the model. Okay, now it should work. So every 1,000, I get the error. You can see it's dropping. Fine. So let's just work with this. So where are we? Yes, we have trained our model. You can see the error have dropped significantly from 2.9 to 0.07. So what next? Of course, we want to plot some let us see how well our model is doing. And you can see here, I made a plot so that you can see how the loss, you can see the loss for both the training set and the test set. The test set is the data that the model hasn't seen before. As you can see, the error is dropping very close to zero. Makes sense because our model is learning. As you can see, the accuracy. The model is, predicting the classes, kind of very, very well. And we did, 10,000 iterations. The code here, this is just nothing more. We just plotted. And the train.errors, these already, I stored these values during the training. So it's not surprising. And as you can see, these are the values here. So at each iteration, I store the error because we want to see the errors and also for the accuracy. And how do we calculate the accuracy? I think it's very straightforward. So we can calculate the accuracy from, created a function. I set a threshold of 0.5, remember? Because now after we predict our X, which is probabilities, I want to ensure that, now let me quickly do something so that you will see what I mean. Let's say we have an array. Let's say these are the probabilities. MP. Oh, no, I want a normal distribution. So these are the probabilities that I print out. Sorry. Okay. Yes, so yeah, I've printed out, is it normal that I want? Between 0 and 1. Okay, that's a uniform. It should be uniform. So I've printed out 10 values between 0 and 1. Now, these are just, think about these values as the output of our model, right? But we don't want to work with, we want to set a threshold that if a certain probability is less or equal to 0.5, let it be 1. And so we can just say probe greater than or equal to 0.5. I'm setting this threshold. So when I print probe now, you can see, you would see false, 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 false. You can see. So what it means is that where it is false, it is going to be 0. Where it is 1, it is going to be true. So easily we can select, we can select the, the places, the points. We can just, like this place now is 0.9. You can see here it to be true. So that's just it. And because we don't want, I think we can just easily sum it. And then what you just get now is the probability. Okay, we can sum. Yeah, not summing. Just want to show off. Okay. So yeah, so that's just basically, you can see the accuracy, and it tries to, now once it's done, then we try to get where this where the predictions and the original values are the same, and we get the mean, right? And then that's all. So yeah, basically that's just it. So here now to evaluate the model, because we are done with the training, you can see the accuracy is kind of good. And remember yesterday we talked about overfitting, bias. The error is low, which means we are not we are closer to what we'd expect, because the error is actually dropping very low. And the goal is to make sure the error goes as low as 0. And we can see the accuracy of the training and the test sets. They are more or less, very close. So there's no overfitting. Imagine the training set was at this point, and the test set was somewhere maybe around 50% or 40% or 30% or something. That's really bad. So it's not learning. So there are some metrics like accuracy, precision, recall, F1 score. These are just metrics, accuracy. We want to know how the model performed, both positive and negative. Positive here, remember, would mean, the presence of malignant tumor and benign tumor. So to find the total accuracy, there's something like true positive. True positive is, indeed is positive and the model predicts positive. And the true negative is that the model, the actual label is actually negative, that is a benign tumor in this case, and it predicts. So to get the accuracy, we sum it, we divide it by the sum of both the correct and the false predictions, and we get the accuracy. Precision is different. We want to know the ratio of the correct positive predictions to the total predicted positives. So that is, we have all the total predicted positive. Out of those positive, which one are actually correct? And this is the formula. So the metric that, there are a lot of metrics. You have the F1 score, which is the harmonic mean of the precision and recall, and it tries to balance the two. So the difference between precision and recall is, recall wants to know the ratio of the correct positive predictions to the total actual positive. This one is the ratio of correct positive prediction to the total predicted positives, right? And that's just the difference. So, so let us print out our accuracy. The accuracy is 95% for the training and 96% for the test set, as you can see. I think I can reduce this to 4 decimal points or something. Oh, okay. I think, okay, I didn't finish. So, is there a question? Are we following? Is it interesting, or is there something? If there are questions, please just talk, because I think I've been the only one talking. It would be nice to really know, until this point, does it make sense? Is it something that that looks intuitive? Can I hear in the comment section? Is it something?
So guys, if you have a question, kindly put it out there. I've been following the comment section. Some of the questions you were answering it.
Okay.
Where you were.
Okay. Someone asked
why you were teaching.
Okay.
I can see.
Okay. Someone asked, until there is no reduction. Well, yes, in a way, because if you even look at this model, it's still reducing drastically. I can bet you that if we can even take it to maybe 20,000 and try to adjust this place a little so that you don't get too many points there, then the error will continue to drop. And the lower the error, the better your model, I can tell you, because that's the goal. We want to push this error. 0 is the least error. Once it is 0, it means that's 100% prediction, 100% perfect. But usually there's no 100% perfect model anyway, unless if it's very obvious and it's very, very obvious that the model can actually learn everything. Yes, so now this is the accuracy of our model. Like I explained, we want to, in this place, after getting the threshold, then the prediction is what the model predicts. Then the Y is of course, the Y is the ground truth, the original, label from our data set. So we just compare both using this equal to statement, and we get the mean. So the mean there is just of course, it's just it's just like, we want to find the average over the number of samples, right? That's just it. So for example, if you have 5 predictions and the model gets like maybe 3 or 4 correctly, so it's just like 4 over 5. So that's just it. 4 over 5, that's about 0.7. So they multiply by 100. So what's next? We are almost done, and we are moving closer. And another way, so here we just test our model. Remember, we want to test our model, and the goal is to test our model now and to see how, so the predict, already there's a predict method in the formula, as I explained. You know what the predict will do, just outputs the probability, nothing more. So when we when we call the predict on the test set, it's going to output the probabilities for each of the samples. And what do I mean? Let me explain. So let me print now the Y predict test. So now when we run this, you can see these are probabilities. Like for example, this is 0.9, this is 0.000. This one is very close to 0. This one is 0.000, very close. This one is 0.999. So, but remember, we don't want probabilities, at least as far as we are concerned. Remember, we don't want probabilities. We want to set a threshold, right? We want to know that, okay, this probability is closer to 0. It's more likely that it belongs to class 0. If the probability is closer to 1, it's more likely that it's close to 1. So what I just did here was, it's very simple. Now, we loop. We say 1 if p is greater than or equal to 0.5. Remember when I started, I said, okay, you can set a threshold. For me, I don't think it's nice to actually, outcode something. We can put the threshold outside. Then, so what I would say is that anytime the probability is greater than 0.5, just replace it with 1. Else 0 for P in Y predictors. Remember, this is the Y predictors, which is in probability. I think I should even put probability here, Y predict probability. Then I will just come here, probability. So now let us print out the Y predict test. So remember, the other time it was printing out probability. So now let's see what the probability. So you can see now it's now, okay, I think I should even print the probability also here so that we will see the probability, so that we'll see the difference. Now, do you now see? Now, remember this first one was 0.9, 0.96, but because of it is more than this, the threshold of 0.5, right? This one would be 1. Now, let's look at this. This one is 0.0. This one is close to 0. So already we know that the first example is 1. The second one is 0. You can see 1, 0. Like that. Like this last one now. This one is exponential minus 13. It's very close to 0. And you can see 0. So you can see now. So we have taken the, we have converted the probabilities to binary class 0s and 1. And yeah, the accuracy is recalled. 95, almost 96%. We actually predicted the correct thing out of the population true labels, which makes sense. So, but aside that, let's also see something. There's what we call conversion metrics. It gives us an idea of how well the model predicts. So now conversion metrics is just a way to show, okay, what is the true class? What is the predicted class? For example, this is the true class. This is the predicted class. This is benign tumor. So now in this case, let us start with the malignant tumor. 68 times the model predicts correctly that an example is a malignant tumor, right? And the true class is actually malignant tumor. Now, for the other one, 42 times, the model predicts that the example is a benign tumor, given that the true class is benign tumor. But only once the model fails, the model it's wrong. It's classified. Just one sample. It wrongly classifies it as a malignant tumor. Just one. Or 42 times it does the right thing. So. And here, 3 times, the model wrongly says, okay, this is a benign tumor. However, it's a malignant tumor. So it's not too bad for a model that, and yeah, in this case, there is what we call true positives or, true negatives. Depends on the problem statement, what you mean by positive, but always on the diagonal is what, you always want. You want to ensure that the numbers in the diagonals are really high, because that's the point where the predicted and the true class intersect, right? So in this case, if this is malignant tumor, let's say this is true positive, which is true positive, and here, so if this is true positive. Here we have false positives, because here the model predicts malignant tumor instead of the malignant tumor. So I think it depends on how we arrange it. I think this is this should be false negatives. Because here the malignant tumor here should be negative, so it wrongly says it's malignant tumor. So this is a kind of false negative. It's actually malignant tumor, right? Yeah, and so this is a false negative. So this is not supposed to be negative. It's supposed to be, yes, it's supposed to be positive. So in this case, we have, here is false positive. So here so the patient actually is, that tumor is a malignant tumor, but the model calls it malignant. I mean, it's a benign tumor. The prediction says malignant, so it's a false positive. I will send some link also to for us to really understand how this confusion matrix works, so that to understand what this entry is. And this entry also, you have to be very careful. You have to be careful about the problem statement. Some positive something bad can be a positive for you. Something good can be a positive for you. It doesn't matter. It just depends on what you want to classify as positive. So if you say, yeah, malignant means like, so if you correctly predict malignant tumor, if it's positive, then you say it's a true positive. Then on the other hand, if you say, okay, malignant tumor is negative, then it's a true negative. And there is one thing called the ROC score, so which also tells us, it also gives us this kind of, it plots the true positive rate against the false positive rate. So usually we want to know, how much, the area under this curve tells us the performance of the model in general. And an area of 1 means perfect, right? Yeah, so this diagonal line here is it's a kind of, this is just the threshold of some kind of, random prediction. So we don't want our model to be at this, but want it to move towards, this point, right? Because here we have the probability of the true positives, and here we have the probability of the true negatives. So as you can see, the true negatives are really, really minimal, almost close to 0. And we have the true positive pointing towards 1. So the model does very well. I'll be happy to receive questions. If it's very interesting, because by next week, we will build on this when we want to start neural networks and deep learning, go into more advanced architecture. So if you have questions, I'll be happy to answer. I think I'm done for today. So I think we are not too far from the. Okay, someone asked, does it give an accurate prediction or what precisely? Well, the issue of accurate prediction, well, of course, there is nothing accurate. For example, if you look at this confusion matrix, one time the model failed, it says the actual class is actually the class is actually benign tumor, but the model says it's a malignant tumor because here it's a predicted class. So it's a kind of it's a false, it's a false positive, like because you want it is wrong. It classifies that tumor wrongly as positive, whereas it's not positive. So it's a false alarm. It's a kind of false alarm, and yeah, and usually, yeah, that is, yeah. So in this case, you cannot say the model is perfect, right? You cannot say the model is perfect. So also in this case, 3 times model failed. Yes. So is there any question? Yes, the video will send it across. Is there a maximum number of predictors according to the sample size when we are running the model? Is there a maximum number of predictors according to the sample size? Well, the predictor here is, in this case, already, the predictor is what these are the predictors. Like the mean radius, the mean texture, the choice of selecting predictors, which is the feature extraction here, is also what we discussed yesterday. These are things that might require also, expert people in the domain, expert domain. Like, for example, you want to build a model and you ask a doctor, "Oh, doctor, please, I have this sample. Which of these features do you think, would be instrumental when I want to?" Because of course, if you go to the hospital, they want to take tests, and they know by certain value if you are likely or you are prone to certain disease. And that is one aspect. For me, I'm not a medical doctor, but of course, because I don't even understand what this mean concavity means, but I'm sure someone in the medical line would understand. So yeah, otherwise, for me, I just use the 30 like at a go, and it works out fine. You can decide to use probably, okay, just 2, let me check, but then you are just doing a kind of random experiment, which doesn't make sense. So most times you want to be sure of what you are doing. You just want to be doing something. Where do we apply this model? Yes, you can, because if you have samples now, if you have models, if you have data set that has this kind of information, like you see the data set outside somewhere, you can just use your model. You can train a model and you can feed in these values, and you can actually predict if that patient has a tumor or not. And it's just like that. Well, by next week, I will do real life application of how we can also deploy. I'll be doing a project on computer vision, and just a simple project on how we can classify handwritten digits. Right, it's a very popular project, like very simple project, at least for beginners. If you're very interested in computer vision, NLP is also very interesting. But I didn't talk about NLP here because I only just of course, I know about NLP, but I'm more interested in computer vision, even though I also use a lot of techniques from NLP, computer vision, and I understand how. But if you also want to go deeper into NLP, during the course of, in the future, we can also organize more specialized, trainings, right? Computer vision, NLP, right? And so there you can go deeply into, some of these cool advanced application, and you find it very interesting. For NLP, we are talking about words, sentences, tokens, you don't want to, in this case, we are just dealing with numbers, right? In natural language processing, we are talking about words or audios or videos, so we have also, interdisciplinary field of computer vision and NLP. Like in the case of video, we have images, like videos, frame, in a kind of 3Ds and 3D frames. And also we have, sounds, which is audio, like languages. So it's really interesting. Next week, please don't miss the class. We'll be doing nice project. And I can promise you would like it, and you can decide what you really want to do and which area, what interests you. And also we need feedbacks on the areas where also subsequent trainings, what we can cover. Is there any acceptance threshold of the algorithm convergence to be fixed? There is no acceptance threshold. The threshold just depends on how well your model performs. In this case, I think for me, the model has performed well. And as a matter of fact, because even the error was dropping drastically, let's like, for your question, probably I would want to increase this to 20,000. I think, so that we can see, also I can increase this to 5,000. Let's see if the model would actually improve. And the idea is to actually check if the model can improve, because just as the question, is there any acceptance? But for me, I don't think there is any acceptance until your model can even perform as I don't know how we call best in this case. But now I'm done. Let's check the accuracy. Yes, okay, I think I'll print it out in this. Initially, okay, here. If you look at now, let's please just try to keep note. This is 97.8 for the training, and this is 96. So now let's run it, 7.896. You can see the training accuracy has increased to 98. The test has increased to 98 by just increasing the number of iterations. So it means that even the 10,000 I did was not even enough. I mean, and you can see so let's even go there. So we will confirm from this confusion matrix. Initially, we had 3 wrong predictions, 3-1. Let's see if it will improve, 3-1. Now you can see it has reduced. So there are the 2 samples here that were wrongly classified. Somehow, they have been, the model has classified them, correctly, right? And this is because of, this place, remember, this place was 69, 67 or something. Was it 68? I think it was 68. Yes. And you can see now it has increased to 70. So initially the model predict a malignant tumor as a benign tumor. But when I increased the iteration to 20,000 from 10,000, it just pushed the right thing. Well, you can see the model has improved. So you can do better. That should be the challenge. I mean, that should be the goal. Can I do better? If I had increased it to 20,000 and it didn't change anything, then I can even still go ahead. I don't know, because for me, I didn't try it. I can say, okay, let's check if the model can even do better. I don't know, I'm not sure. But if it doesn't, of course, model cannot be 100% perfect, right? So let's check if we can even get a better result from So 10,000. I think I did it now for 30,000. Okay, now we are done. Yes. So let's actually check. Let's check the accuracy. 98, 98. Okay. Yeah, I don't think it improves, but I don't know. Let me confirm from this confusion matrix here. At least we have 1. Okay, it doesn't improve. So you can see now. So for your question, you can see this illustration just explains, if there is a threshold, if there's an acceptance threshold for the algorithm convergence to be fixed. It's not fixed. Just keep trying. Can I do better? Can I do better? The goal is to ensure that this is 0 and 0. You want this to be correct. Okay, thanks a lot. I think I'm done for today, and I'm happy to to have presented this this particular. So just think about
great
this.
Work, man.
Yeah.
I said great work today, man.
Yeah, thanks. So this is just a way to get us into the topic. There are also very interesting things you can do, and one of the things I always want to do, and for me, I always like to do is after this class, try to understand what the codes, exactly. Try to look at the algorithm here. And that was why I focus on algorithm. Algorithm is very important. Look at the algorithm, look at how it was coded, right? And look at, so what is the coding? How does, so the connection, is it too far? It's not too far. These formulas are just what we implemented. And that is why basic Python programming. Well, as you go higher, you might not actually require, writing some of these codes. If you're not, there are other nice, but regardless of the kind of framework you use, I think it would be nice that you know how this thing works in the background, right? From the formula, you don't have to be an expert in math, just understand how some of these formulas. So I'm going to add the link also to some of these formulas. Well, I actually proved it here in the slide from the derivation of the logistic regression, the Bernoulli distribution. I can also attach some video links. If you are very interested, if you're interested in how some of the math work, for me, I like math because I come from a math background. So aside the fact that I can write, you can write programs or codes like this. It's also good because how can you write what you don't even know? I mean, you can't even write what you don't know. If you see this kind of formula now, the question is how did this formula add? All the libraries you would be using, whether you are importing them, these formulas are in the background. For example, the linear, the logistic regression, it's a package, it's from the sklearn library. You can just use it without writing all of this code. Just feed in your data, your input and your output, and it gets the result. But of course, I think now it makes sense that you know how this thing works. Yeah, I think I'm done. Thanks a lot. AUC been added. Please share more light. Okay, someone said I should share more light. So I think
maybe next week, because we don't want to go over too much. We're already 60 minutes in. Yes. I know this thing is very, very interesting. And when you start it, you don't want to end it.
Okay, yeah. For the question, I'll talk about it next week.
Probably next week. Maybe they can keep the question coming on the group.
Okay, yes.
So please just go to the WhatsApp group and put in the questions. We get them all. Because if we leave Austin here, he's going to go for 10 hours. Okay, this is what he has a PhD in. He loves it like if we leave this guy here, he goes in for 10 hours and you guys will be like, because this is what he loves doing, you know. It is what he lives by. So I think we just, you know, we keep it short here.
By next week, we'll continue, but we'll go into more advanced, go into deep learning.
Okay. So if they have any questions, they should ask on the WhatsApp group.
Yes,
we can take it from there. Please,
okay,
it's important. Thank you. Well done, guys.
All right, thanks, guys.
Well done.
See you next week.
Well done, everyone.
All right, see you guys.
All right, thank you. Bye, everyone. We'll share the recording very soon.
Thank you.